Hi guys, and welcome to today's class. As I've mentioned, is that last week we were testing hypothesis for single samples. Now this week we shall be looking at hypothesis testing for two samples, and we shall be assuming that the samples are independent. And our starting point will be the testing we'll be testing the value of the difference of two population means, the difference between two population means. So we shall start by considering two random samples. So we start by saying consider two independent random samples, of sizes n1 and n2 from populations which are believed to be normally distributed. So from a normal distribution with a mean mu1 and variance given by sigma 1, and the other sample is coming from a normal distribution with mean equal to mu2 and variance equal to sigma 2 squared, respectively. So we're assuming that these two samples are coming from, each is coming from normal population. Okay. Then the hypothesis to be tested is, so testing the hypothesis, we want to test the hypothesis that H naught is such that mu1, the mean of the first population, minus the mean of the second population is equal to some constant, some delta. Okay. In most of the cases, this delta will be 0. So we'll be talking about H naught, that mu1 minus mu2 is equal to 0, which basically is saying that mu1 is equal to mu2. In most of the cases, the value of D, this is your delta, this is the value of your delta. This value here will be equal to 0, but it can be replaced by any other value. So that's why I put it at delta, so it can take any number. Okay. So there are two scenarios, just like we saw in the case of single samples. So we have the first scenario when sigma 1 squared and sigma 2 squared are known. We use the Z statistic. We assume that the statistic, the population means are normally distributed. Okay. And the Z statistic in this case is defined by Z is equal to X bar 1 minus X bar 2. You take that minus delta divided by the standard error for the difference of two sample means, which will be given by sigma 1 squared, divided by n1 plus sigma 2 squared over n2. So when sigma 1 and sigma 2 are known, we use the Z statistic. And the Z statistic is given by that, where the divisor here is the standard error. So this is the standard error of X bar 1, X bar 2. The denominator here, which is equal to sigma 1 squared over n1, 2 squared over n2. Okay. And the second scenario, number 2, is when sigma 1 and sigma 2 are unknown. First is that we estimate them. Using S1 squared and S2 squared. Those are the sample variances, or the respective sample variances, respectively, full stop. And then there are two scenarios there. If the samples are large, we use the Z statistic. Defined above. So if the samples are large, we use the Z statistic. But number 2, if the samples are small, the samples are small, we use the test, we use the t-statistic. We use the t-statistic, but there's an assumption which must always be satisfied for us to use this t-statistic. Okay, so under the assumption, so if we assume that sigma 1 squared is equal to sigma 2 squared, that is, if we assume that the population variances are equal, we use, so we say that the common variance, which is known as the pooled variance, is used, which is denoted by, let me say this, the pooled variance denoted by SP squared, the pooled variance, close brackets there, is used. So if we assume that the variances of the populations are equal, that is sigma 1 is equal to sigma 2, then we obtain a common variance for the two samples, which is technically known as the pooled variance, denoted by SP squared. So in such a case, the test statistic, which we are calling the t-statistic, will be t is equal to x bar 1 minus x bar 2 minus the delta divided by the standard error, and the standard error in this case will be the square root of SP squared 1 over n1 plus 1 over n2, which can be rewritten as, we can factor out, we can distribute the square root in the denominator, and then you have x bar 1 minus x bar 2 minus delta divided by S of P, multiply this by 1 over n1 plus 1 over n2. So we can push the variance outside after taking square root, becomes the standard deviation. Okay. So where SP squared, where the pooled variance is given by n1 minus 1, multiply this by s1 squared plus n2 minus 1 multiplied by s2 squared divided by n1 plus n2 minus a 2 Okay, so where we know for the t distribution, we must always have the degrees of freedom, and the divisor here is our degrees of freedom, where the degrees of freedom is equal to n1 plus n2 minus a 2, where the degrees of freedom is n1 plus n2 minus a 2. Okay. Example. So the example says that the average blood pressure for a control group, which you are denoting by C, of some 10 patients was 77 units. Then the average blood pressure in a similar group, which you are denoting T, of 10 patients on a special diet was 75 units. Then you are asked to carry out a statistical test to assess whether patients on the special diet have lower blood pressure. And you are given this information that summation of the CI squared is equal to that value, and then the summation of T squared is given by that. So let's solve the question. Solution. So we are given the following information. So we are given that the number of observations in the first sample, or N1, is 10, and also N2 is 10. Then we are given that the mean, or the average, in the first sample is 77, and X bar in the second sample is 75. Then from the information given here, Of course, when you look at this question, we are not given the standard deviations or variances. So that means we are going to use the information given to obtain the variance of the first sample and variance of the second sample. So we know that variance is given by summation of, I'm using x as my variable of interest, x minus x bar squared over n minus 1. Okay, that's a formula that that's a definition of the variance, which we can simplify as summation of x squared minus n x bar squared divided by n minus 1. So we shall be using this version because of the information that we are given. Because of the information that we are given here, we shall use this information because we have the square of the variable of interest. We also know the number of observations in every sample, and we know the mean of every sample. So let's get the variance of the first sample. We are going to denote it by S1 squared. So in this case, we shall be using summation of Ci squared minus n multiplied by the mean of C squared divided by n minus 1. So in this case, we shall have 59,420 minus the size of the sample is 10. Then this mean is 77 divided by 10 minus 1, which is 9. Okay. Then the second sample will have this variance. This is a summation of t squared I. I'm keeping the notation simple. I know I should be saying I is equal to 1 all the way to n, to 10 in this case. I don't need to say that for now. Minus n, then we have t bar squared divided by n minus 1. So in this case, we have 56,390. Is it so? Yeah, 56,390 minus this is 10 multiplied by 75 divided by 9. So when you simplify that, you will get this is 14.4, 4 is recurring, and the next one is 15.5, 5 is recurring, so I can stop at that point. So those are the sample variances. Those are the estimates of sigma 1 squared and sigma 2 squared. Okay. Then we also need to obtain the pooled variance SP squared, which is N1 minus 1. Then we have S1 squared plus N2 minus 1, S like that, divided by N1 plus N2 minus 2. So we need to simplify that. So this will be a 9 multiplied by 14.44 plus again a 9 times 15.556 divided by 18. So if you simplify that, you'll get 14.9999. Looks like that, huh? Before I round off, 7778. And we also need to say the degrees of freedom, because we know we shall be using the t distribution because the samples are clearly small. And in this case, we are assuming that the variance of the first population is equal to the variance of the second population. So the degrees of freedom will be 10 plus 10 minus 2, which is 18. All right. Okay. So now with this information, we can define our hypothesis. So the hypothesis to be tested is so we are testing H naught, that the mean of the first population is equal to the mean of the second population. So here we say mu1 is equal to mu2. We are testing that they're equal, and we are testing that against, so H1 is always guided by the question. So, but we know that we shall have a mu1 and a mu2. So when we check the question, we shall know the kind of relationship that is expected. I think we have a question. So let's hear the question. Yeah, thanks for the observation. We are missing the squared, so I've put it. We are missing the squared. X, the mean should be squared, but the answers will not change. Okay, the answers will not change. I hope that should be okay. So we were at the point of defining the hypothesis to be tested, and the null hypothesis is always given by that. Then the alternative hypothesis will be guided by the question. So here in the question, we are testing, carry out a statistical test to assess whether patients on the special diet have a lower blood pressure, where the guys on the treatment group have a lower blood pressure. So we are testing whether the second value of mu is smaller. So that means we shall be having something like that. We're testing whether this value here, this is the treatment group, and then this is the control group. So we're checking whether the mean of the treatment group is actually smaller than the mean of the control group. So this is calling for an upper tail test. So this is calling for an upper tail test. It's calling for an upper tail test like this. This is 0. And we shall be assuming that alpha is, are we given alpha in this question? So we're not given alpha, so we shall be assuming 5%. 5%. And we're using a t-tail, one tail, let's call it an upper tail t-test. An upper tail t-test at alpha is 5%. T-test at alpha is 5%. So you have the option of getting alpha, the critical value of t here. So we need t critical, which you can get from your tables, or you can run a quick R code. You can run a quick R code to obtain that. So let me display the tables. This is a 5% upper tail test. So let me display the tables. So these are the T tables. We need the critical value. The degrees of freedom is 18. And then, so 18 degrees of freedom should be this row here. 18 degrees of freedom is this row. Then we check the column corresponding with the alpha that we are using. So these are the values of alpha. So these are the values of alpha. And in this question, we are using alpha is 5%. So we need the critical value corresponding to that, which is this value here, 1.734064. Okay, so that's the value we need there. So 1.73. So this is 1.73 for something. Okay. Alternatively, you can use R to generate the critical value, and in this case, the R code will be, you're looking for that quantile. So Q of T, then at what level of significance? At 5%. This being an upper tail, we need 0.95. At how many degrees of freedom? 18 degrees of freedom. Okay, so that gives you the value that we obtained from the tables. That gives you the value we obtained from the table, 1.734064. Okay, so once we have set up our critical region, so this is our critical region. The shaded part is our critical region or the rejection region. Then the next thing is to obtain in this case T calculated. The T calculated, which will be given by x bar 1 minus x bar 2, okay, divided by the standard error of that difference, which will be given by S of P multiplied by 1 over the square root of this plus 1 over, like that. Okay. Then x bar 1 is 77, x bar 2 is 75, divided by, we have SP, so I'll put all of them inside the square root. So square root of, we have 14.99 something, very close to 15. Multiply this by 1 over 10, like that. So we can simplify that. So let's simplify that. So we obtain that the calculated statistic is 1.154701 something, etc. So now we have the calculated statistic and the critical statistic. If you try to place this calculated statistic on this distribution here, this value will be in the acceptance region. Okay, so this value will be somewhere here, like 1.15, which is the acceptance region. So that tells us that we are supposed to, we shall fail to reject the null hypothesis. So let's observe that the calculated t statistic, the calculated t statistic falls in the acceptance region. Falls in the acceptance region. Falls in the acceptance region. So that means we shall fail to reject the null hypothesis. Thus, we fail to reject. We fail to reject H naught that mu1 is equal to mu2 in favor of H1 that mu1 is greater than mu2 at the 5% level of significance. We fail to reject the null hypothesis at the 5% level of significance. So what conclusion do we make? We say that, therefore, it is reasonable to conclude that that patients on the special diet have the same blood pressure. They have the same blood pressure as those in the control group. Those in the control group. That's the conclusion. So that means that the mean in the two groups is the same. There's no evidence to show that the means are different. Okay. Any question about that? So if there's no question, let's try this exercise at home. Huh? We have a car manufacturer runs tests to investigate the fuel consumption of cars using a newly developed fuel additive. 16 cars of the same make and age are used, 8 with the new additive and 8 as controls. The results in miles per gallon of a track test under regulated conditions are as follows. So here's the data, and the questions are given down here. So there are two hypotheses to be tested. Roman 1, where you are testing whether the difference is actually positive, that is mu1 is less than mu2. And in the second scenario, you are testing whether the difference is actually equal to 6. So you'll use a similar approach to solve that exercise at home. So moving on, we shall now be looking at testing the value of the ratio of two population variances. And the assumption here, just like we did in the case of the t distribution for two populations, we shall be assuming that variance of the first population is equal to the variance of the second population. But before we reach there, let's say the following. Consider a situation where two independent random samples of sizes n1 and n2 are chosen from two normal populations, two normally distributed populations. So mu1 sigma 1 squared and normally distributed population with mean equal to mu2 and variance equal to sigma 2 squared respectively. So assume two samples of given sizes there are chosen from those two populations. Okay, so let's denote the respective sample variances. Denote the respective sample variances by S1 squared and S2 squared, full stop. Okay, so the hypothesis to be tested here will be H naught, that sigma 1 squared is equal to sigma 2 squared versus, and in this case we have H1 given by sigma 1 squared is different from sigma 2 squared. So here we are testing whether they are the same or they are not the same. Okay, because of the assumption that I just mentioned, that in this context we shall be assuming that sigma 1 is always equal to sigma 2, or the two populations have equal variance. Okay, so now the alternative hypothesis will be to check whether that has been violated. Okay, so the test statistic under the null hypothesis so that just means when we assume that the variances are the same, so this will be given by an F statistic in this case. So we can call it F calc. I'll just be calling it F, which is equal to S1 squared divided by S2 squared. Remember this item here is coming from this more general item, that is S1 squared over sigma 1 over S2 squared over sigma 2 squared. When we assume that this item here is equal to this item here, then we shall end up with this item. If we assume that those two values are the same, if we assume that sigma 1 squared is equal to sigma 2 squared, that is, if we assume that the null hypothesis is true, then we have the F statistic, which is defined by that. Okay, so here we use the F statistic, where the degrees of freedom are given by n1 minus 1 for the numerator, and this is for the numerator, and n2 minus 1 for the denominator. But it's good for you to note that you can always switch. It doesn't have to be S1 over S2. You can reverse and say S2 squared over S1 squared, and the conclusion will always be the same. So if that happens, you will be switching these values appropriately. Okay. So this statistic here follows an F distribution with n minus 1, n1 minus 1, and and n2 minus 1 degrees of freedom. Okay, example. So here we're considering the data given in the previous example, the one that we just solved. And the question here is to test whether the variances in the two populations in example 11 can be considered to be equal. Then I've extracted the information from that example. The size of the first sample was 10, as well as the size of the second sample. Then sample variance of sample 1 was 14.44. Then the variance of the second sample was 15.55 something. Then if we take alpha, or we let alpha to be 5%, then now at this point we can solve the question at hand. So solution. So the starting point is to define the null hypothesis. So here we are testing whether, so H naught is that whether sigma 1 squared is equal to sigma 2 squared. And we are testing that versus H1, that the two values are different. So sigma 1 squared is different from sigma 2 squared. Okay, which is calling for a two-tailed test. It is calling for a two-tailed test. Okay. two-tailed test. And in this case, we shall be using the F distribution, so which we may want to sketch like that. We may want to sketch it like that. So usually for the F distribution, this is where you have your alpha. So in our case, because it's a two-tailed test, this will be alpha over 2. Then we shall be having the remaining alpha over 2 here. Alpha over 2 there. Okay, so we need these critical values here. We're going to obtain them in a few minutes. But before you obtain them, let's get the F, the calculated statistics. So F calc, which will be given by S1 squared over S2 squared, which is 14.444 divided by 15.5556. Remember, I could have switched them. I could have 15.55 as the numerator and 14.44 as the denominator. In other words, I can have S2 over S1. So it doesn't change the conclusion in this case. So the calculated statistic, if you use your calculator, will get 0.928 something, 86, so something like that. Now we need to obtain the critical values, and I'll prefer that we obtain the values, the F statistics here, the critical F values here, so F crit, and even here F crit, we obtain them using R. So let's quickly go to R and obtain those critical values. So I need the quantile F. Then I'll start with the upper value. The upper value will be 0.975. So that's the value I'm looking for. Sorry. Sorry, the degrees of freedom in for the numerator will be 9, and for the denominator will also be 9. So when you run that, you will get 4.025. Huh? Let's say 4.026. 4.026. Huh? Then the lower tail will get. I'll use the same code, huh? But now the cumulative probability here. So this should be 0.025, 0.025 like that, the same degrees of freedom. So I'll get the value is 0.2483. So 0.2483. So using R, we have seen that the lower value is 0.24884, something like that. So 0.2484. So those are the critical values. Alternatively, you can use the tables. You can use the F distribution tables to obtain those critical values. But of course, when we have a two-tailed test for the F distribution, it becomes a little bit tricky. So let's see what happens there. So, sorry, we are not here at 5%. So these are the F tables. The degrees of freedom are 9, both for the numerator and denominator. So we should be working the last column here. This is for the numerator. And then on this side, we have the degrees of freedom for the denominator. So, and then here, this column here represents the different levels of alpha. So for instance, this is alpha is 10%, alpha is 5%, alpha is 2.5%, alpha is 10%, alpha is 1%, and so on and so forth. So these values are replicated here so as to take care of the degrees of freedom. Okay. So in our case, we need 9 degrees of freedom, both on the numerator and the denominator. So 9 degrees of freedom are here. And then our distribution looks like this now. We're looking for this value. This being a two-tailed test, so we need alpha over 2, which is 2.5%. That means the other value will be here, which is alpha over 2. So the tables that I'm displaying here are giving you this value here, this one, F crit. So in our case, we have, so we should be working with 2.5. So I'll be working with this, I'll be working with this value here. So let me underline so that we don't miss it out. So I'll be working with that. So 9 degrees of freedom for the denominator and also for the numerator. So this is the critical value, 4.03. 4.03. So this is 4.03. Now the lower value here, the lower value is given by F divided by this value here. So in this case, you'll have 1 divided by, the lower value will be 1 divided by 4.03. And if you quickly do that, that will be 1 divided by 4.03. We'll get 0.248 something, similar to what we got from the from R. So if you're going to use the tables, you just need to get the upper value, and to get the lower value, you take 1 over the value in the upper table. So that's basically it. So I think we have the critical values, we have the critical region. So now we can make our decision. So clearly, this value here falls in the acceptance region. As you can see, it is falling here, 0.928 something. So that's what we observe. We say that the observed F statistic falls in the acceptance region. Falls in the acceptance region. That tells us what we need to do with the null hypothesis. Okay. So so we fail to reject. We fail to reject the null hypothesis. We fail to reject H naught, that sigma 1 squared is equal to sigma 2 squared, in favor of H1, that sigma 1 squared is different from sigma 1 squared. We fail to reject the null hypothesis, and alpha is at the 5% level of significance. So that means that, so thus, there is evidence, there is insufficient evidence to help us conclude that there is no difference. There is no difference in the variances of the two populations, in the variances two populations. So the two populations have equal variance, in short. From the evidence we have, the two populations have equal variances. Okay. Any question there? So next we shall be looking at hypothesis testing for the difference between two population proportions. And as you are aware, populations usually come from what we call binomial distributions. And for us to assume that the statistic coming from a binomial distribution is normally distributed, then the size of the sample must be large. So you notice that the test statistic will be assuming normality if the samples are large. And that's why you will not find us using the T statistic for proportions, because for proportions, N must be large for us to assume normality. So that's one key thing that you need to note, that the N, the size of the sample here, must always be large. So let's say for large samples, we can perform both one-tailed and two-tailed tests on the difference between two binomial probabilities as follows. Okay, so we start by letting n1 be the number, let n1 be the number of trials, and then P of success be denoted by pi1, and x1 be the number of successes, corresponding to the first large sample. Let those be the symbols corresponding to the first large sample. N1, pi1, these are comma, pi1, x1, yeah, like that, for the first sample, which must be large. Then we also similarly let N2 be the number of trials. Then P of success is equal to pi2, and x2 be the number of successes corresponding to the second large sample. So we have two large samples from a binomial distribution. Okay. Then the objective is to test the hypothesis. We test the hypothesis. We say H naught that pi1 is equal to pi2. In other words, that is the same as saying that pi1 minus pi2 is equal to 0. That means the difference between the two population proportions is equal to 0. Okay. So to test this, we use the statistic. And here we are assuming normality based on the central limit theorem. So Z calculated, which is equal to P1 minus P2 divided by the standard error will be given by, this is a P hat, that's P hat multiplied by Q hat. Then multiply that by 1 over N1 plus 1 over N2 close brackets. Everything in the divisor is under square root. Okay, so where P1 and P2 are the respective sample proportions. So P1 is the proportion of the first sample, and P2 is the proportion of the second sample. Then we have this item here we are calling P hat. P hat is equivalent to the common proportion for the two samples. If you were to mix the two samples and come up with one larger sample, then P hat is the combined proportion, and it's given by. So the definition here is analogous to what you saw maybe in what you call combined mean. If you remember what you call combined mean, the definition of combined mean, which is given by, you can denote combined mean by that, is given by N1 x by 1 plus N2 by 2 divided by N1 plus N2. So if you have two samples and you know the size of the sample and x bar for each of the samples, then you can obtain the overall mean of the two samples combined using that formula. And it's the same formula that we shall be using here, but now in the context of proportion, not in the context of x bar. So we have N1 P1 plus N2 P2 divided by N1 plus N2. So if you have two groups, that's how you get the combined proportion for the two samples under consideration. Okay, so this is the overall. It's the overall sample proportion, of success, and Q hat is 1 minus P hat. So you just need to obtain P hat, then Q hat will be easy to see. So in this case, using the same idea, we can say that Q hat is the overall sample proportion of failure. Okay. So let's have an example. So the example says that in a 1-year mortality investigation, 25 out of 100 90-year-old males and 20 out of the 150 90-year-old females present at the start of the investigation died before the end of the year. So we are taught to assume that the number of deaths follow the binomial distribution. And then the question is, test whether there is a difference between the male and female mortality rates at this age. Okay. So solution, let's see, what are we given? We are given the number of successes in the first sample, which is 25. Then we're given the size of the first sample, N1, which is 100. We're given the number of successes in the second sample, which is 20. We're given the size of the second sample, which is 150. Okay. Then we can let pi with subscript m, let pi with subscript m and pi with subscript f be the population proportion of males and females respectively. The population proportions of the males and females respectively. Okay, yeah. Okay, so we need to test the hypothesis that H naught, that pi of male is equal to pi of the females. Against the hypothesis that H1, we are going to have that, but we'll be guided by the question to know which kind of symbol to put there. Test whether there is a difference between the male and female mortality rates. So we're testing whether there is a difference, whether they're equal or they're different. So that calls for a not equal sign, which is calling for a two-tailed test. Okay. Two-tailed test, assuming the standard normal distribution at alpha is 5%. So we say alpha is 5%, then the Z value here will be minus that, and here will be plus 1.96. So we have set up our critical region. Okay. Then from there we can obtain our Z calculated. And we've said this will be given by, this will be given by the formula above. This will be given by the formula above. I don't want to repeat the formula. But as you notice in the formula, we need to compute the overall proportion of success. So before we compute the test statistic, so let's put this one on hold. So let's obtain our P hat from the given information. And in our case, we just need to take x1 plus x2 divided by n1 plus n2. Because you know that x1 is n1 p1 and x2 is n2 p2. Okay, so in this case we shall be having 25 plus 20 divided by 100 plus 150. So our p hat in this case will be 0.18. That means our q hat will be 1 minus 0.18 is 0.82. And now we can compute the statistic. So zcalc, in this case, sorry, I think we should also have calculated, we should have calculated the P1 and P2. So P1, so from here we get P1, P1 is X1 divided by N1, and P2 will be the number of successes there divided by N2, which will give us 25 out of 100, 0.25. From the second sample, we have 20 out of 150, which will give us 0.133. So I think now we have everything that we needed. We have P1 and P2. So the Z calculated in this case, in this context, will be 0.25 minus 0.133 divided by, we have a square root, 0.18 times 0.82, 1 out of 100 plus 1 out of 150. So that's what we need to simplify. That's what we need to simplify. So we observe the calculated statistic in this case is 2.35 like that. Okay, so that's what we want to compare with the critical values, 2.3 here and 1.96. So here you notice that 2.3 something is deep in the rejection region, 2.359 something. So we observe that the calculated statistic is in the rejection region. Is in the rejection region. So that means we are going to reject the null hypothesis. So here we observe that the calculated statistic Z value, which is 2.359, falls in the rejection region. It falls in the rejection region. So we reject the null hypothesis. We reject H naught that phi of M is equal to phi of F in favor of H1 that pi of M is different from pi of F at the 5% level of significance. So we have rejected the null hypothesis. So that means there is reasonable evidence. So that means we have reasonable evidence to conclude that the first group, that males, let's say these, that male and female mortality rates are different. That male and female mortality rates are different at this age. The mortality rates are not the same, are different at this age. So you could have arrived at the same conclusion using p-values. I think for now you should be able to use the p-values quite comfortably to come up with a similar conclusion there. Okay, please remember that this is a two-tailed test. So when you run the code, you must multiply by 2 so that you get the probability on both tails. So you can try that. You can try that after class. So let's have this exercise to practice. You practice this outside class. So finally, let's look at hypothesis testing for the difference between two Poisson means. And we shall start by saying that, or by considering, so let's say consider a situation where 2 independent random samples of sizes n1 and n2 from these distributions from Poisson with lambda 1 is lambda 1 and Poisson lambda 2 distributions respectively. Then you say that when n1 and n2, so this assumption must be there. So when n1 and n2, you can also say and or the parameter values, the parameter values, these are the lambda 1 and lambda 2. So, but we're saying basically when n1 and n2 are large, we can use normal approximations. We can use normal approximations. Just like we mentioned in the case of binomial distributions, for you to approximate the binomial distribution using a normal distribution, the sample must be large. The same case with the Poisson distribution. For you to use a normal approximation, then the size of the sample must be large, okay? Sometimes you can also say even when the parameter values are large, okay? So the hypothesis to be tested in this context will be H naught, that lambda 1 is equal to lambda 2, and the test statistic in this context will be Z-calc, assuming the standard normal distribution. I'll use this denotation, lambda 1 bar minus lambda 2 bar divided by the standard error there, which will be given by the square root of lambda with a hat into 1 over n1 plus 1 over n2. So we have that where lambda 1 bar and lambda 2 bar the sample estimates of lambda 1 and lambda 2 respectively, where lambda 1 bar and lambda 2 bar are the sample estimates of lambda 1 and lambda 2 respectively. Full stop. Then just like we saw in the case of binomial distributions, we have lambda hat equivalent to the p hat. So this is a common, the common parameter for the two samples. So this is given by n1 lambda 1 bar plus n2 lambda 2 bar divided by n1 plus n2. So this is the common lambda for the two samples. Okay. Like that. So let's have an example. So let's look at this example. The example says that in a one-year investigation of claim frequencies for a particular category of motorists or drivers, there are 150 claims from the 500 policyholders aged under 25 years. And there are 650 claims from the 4,500 remaining policyholders. And you're told to assume that the number of claims made by individual motorists in each category has a Poisson distribution. Then you're asked to test at the 1% level of significance whether the claim frequency is the same for drivers aged 25 and for drivers aged over 25. Okay. Solution. So let's do this. Let's denote the younger and older groups by A and B respectively. So A represents the group 25 years or below, and then this is the group which is more than 25 years of age. Okay, so we are testing the hypothesis that H naught, that lambda of group A is equal to lambda of group B, and we are testing that against H1. So we have lambda A, and then we have lambda B. So we shall be guided by the question. We are testing, we are told to test at the 1% level of significance whether the claim frequency is the same for the two groups of drivers. So either they are the same or they're different. So here this is calling for two-tailed test. Okay. Then at the 1% level of significance, so we have something like that. So at the 1% level of significance, what is the critical value of Z there? So we can quickly get those values from R. So we have Q norm 0.97, no. So what value are we using here? We have 1%, so 1% like that, 1 minus that. So divide by 2. Yeah, so at the 1% level of significance, if we are having a two-tailed test, then on the upper tail, we shall be having, we need the quantile that corresponds with this cumulative probability, 0.995. And the statistic there is 2.5 something. Is that correct? No, there's a problem somewhere. Yeah, it's okay. The values are okay. So let's proceed. Let's proceed. So this is plus and minus 2.58 approximately. Here minus 2.58. So after that, we need to obtain the Z calculated, which will be given by, in this case, we have P1 minus P2 divided by P hat, Q hat, 1 over N1, 1 over N2, everything under square root. So we need P hat. We really have, we need P1 and P2 as well as P hat. So P1 is the proportion of success in the first sample, and the proportion of success here will be given by the number of claims in the first sample, which is 150 out of the total number of policies. So in this case, we say that P1 will be equal to, so we are calling it lambda 1. Sorry, let me for consistency, let me use the same notation there. So this will be, we can call this one P of A minus P of B, like that. Then N of B, sorry, N of A, and then N of B, like that, for consistency. So the first one will be, what value is this? Oh, sorry, I think I'm making a mistake here. We're in the Poisson context. We're in the Poisson context, not the binomial. So the formula that we're using here, sorry, is Z calc will be lambda 1, which you can call lambda A, minus lambda of B, divided by, we have lambda hat 1 over N of A minus 1 over N of B. This one you have square root. So lambda bar of A will be given by the number of claims in the first type of policy, and this will be 150 divided by 500, and then the mean number of claims in the second one will be, how many are this? This will be 650 divided by 4,500. 4,500. Then lambda hat will be given by the number of claims in the first group, which is 150, plus the number of claims in the second group divided by 500 plus 4,500. So let's simplify those values. So lambda A in the first group will be 0.3, and then in the second group we should be having 0.14 for recurring. Then lambda hat will be 0.16. So I think we have all what we need. We know the size of the sample in each case. So n of A is 500, and then n of B will be, or is 4,500. So the Z calculated in this case will be given by 0.3 minus 0.144 recurring divided by the square root of 0.16 multiplied by 1 out of 500 plus 1 out of 4,500. So that's a Z statistic, or the calculated statistic. Then you should get your Z calculated value as 8.249582, something like that. Okay, so that's the value we use to compare with the critical values up here. And clearly, you notice that that value is deep in the rejection region, 8.249 something. Is deep in the rejection region. So that means you are going to reject the null hypothesis in favor of the alternative hypothesis at the given level of significance. So we notice that the calculated statistic falls in the rejection region, or in the critical region. Huh? So that means, so we reject this H naught, that lambda of A is equal to lambda of B. We reject that null hypothesis in favor of, so we reject the null hypothesis in favor of the alternative hypothesis H1, that lambda of A is different from lambda of B at the, which percentage? At the 1% level of significance. At the 1% level of significance. So with that, now we can make a conclusion based on the information we have. Therefore, it is reasonable to conclude that the claim frequencies, it is reasonable to conclude that the claim frequencies are different, are different for the younger and the older motorists, for the younger, older motorists or drivers. So that's the conclusion. So the claim frequencies are different from the evidence that we have. Okay. So alternatively, you can use a p-value. So you can use your R code you can use R to generate a p-value for that hypothesis. So if you use the p-values, the R code will be given by this. And the exact p-value is this number here, which is extremely small, which means that we have very strong evidence against the null hypothesis. So we're going to reject the null hypothesis and end up with the same conclusion, And that is the end of today's lecture. Let me know if there are any questions.